Hello, I'm Junpeng Zhao from Nanjing University. My topic is verifying optimizations of concurrent programs in the promising semantics. Optimizations of concurrent programs are error-prone. On the one hand, sound optimizations for sequential programs may be unsound with concurrency. Consider the following example. We use x and y to represent shared locations. They are valued 0 initially. A location taking a red subscript means that we use C11 atomic primitives to access such location. Otherwise, the memory access is non-atomic. For this program, we find that y will never be written in the loop. So the read y to the register r is a loop invariant. Loop invariant code motion will allocate a new register r prime to save the result of reading y, and then replace the read y in the loop with the value in r prime. Such optimization is correct for sequential programs, but may be incorrect for concurrent programs. For example, loop invariant code motion is unsound in C11 concurrency. Consider that there is another thread writing 5 to y. We can find that the target program contains read-write reads on a session y, and has undefined behaviors in C11 model. However, for the source program, since there is no write for x in the program, the relaxed read x always returns 0, and the loop body never executes. So, read y to r will never be executed, and the source program is data-free and will print 0. On the other hand, the soundness of the optimizations for concurrent programs is related to specific memory models. For example, such transformation is not a counterexample in the promising semantics, which gives semantics to receive programs. So the target program is not undefined behavior in the promising semantics. Like read y to r in the source program, assign r prime to r in the target is unreachable, and the target program also prints 0. Actually, we have proved that loop invariant code motion is sound in the promising semantics in our work. The common optimization loop invariant code motion, which is sound for sequential programs, is unsound in C11 model, but sound in the promising semantics. So it's important to verify optimizations in specific memory models. Prior works on verifying optimizations for concurrent programs either use strong memory models such as SC and TSO semantics, or only work with code snippets. However, optimizations on code snippets just work with local syntactic code patterns, and may not apply for real-world optimization algorithms, which rely on semantics information of contexts and require various program analysis. In this work, we verify optimization algorithms in the promising semantics 2.1. It's an operational semantics for C11-like memory models, and implementable for mainstream hardware platforms, and has no out-of-thin-air values. In more detail, we make the following contributions. First, we develop a verification framework for optimizations in the promising semantics 2.1. The correctness of optimizations is defined as a thread local simulation, which allows separate compilation. We use two verification techniques to simplify proofs. Define the simulation on a non-preemptive semantics to reduce interleaving, and considering only write-free source programs. We allow read-write-receive programs to support reasonable optimizations such as loop invariant code motion in LVM. We verify four optimization algorithms: constant propagation, common subtraction elimination, loop invariant code motion, and dead code elimination in the promising semantics. We first adapt their corresponding sequential optimizations for the promising semantics by carefully allowing optimizations across certain C11 atomic primitives, and verify them in our framework as well as in the cockproof assistant. In the following introduction, we will first give an overview of the promising semantics, then introduce our thread local simulation. Finally, we introduce the non-preemptive semantics and write-read freedom. The memory in the promising semantics records all historical writes as timestamped messages. Initially, each location has an initial message valued 0. Consider a sequence of memory writes on the right side. When executing write 1 to the location X, the promising semantics will select an unused timestamp to insert a new message valued 1 at the location X. Similarly, write 3 to X will add a new message valued 3 at the location X. And write 5 to Y inserts a new message valued 5 at the location Y. A thread in the promising semantics can read more than one prior writes. It's necessary to model the store buffering behavior shown on the right side. To model the store buffering behavior, each thread has its own view on the memory, which records the last observed timestamp on each location, and can read any message at or later than its view. Initially, each thread view records the timestamps of the initial messages. We consider that the thread T1 writes 1 to X first. In this step, we just care about the memory on the location X. The execution inserts a new message valued 1 at the location X. Similarly, T2 performs write 1 to Y by the same way. Then we consider that T1 reads the location Y. As we have introduced, a thread can read any message at or later than its thread view, so it can return 0 or 1. We can find that although T2 has already written 1 to Y, T1 can still read the initial value 0 of Y. For the same reason, read X in T2 can also return 0. In the promising semantics, a thread can promise its future writes. It's necessary to model the load buffering behavior shown on the right side. Let's see how the promising semantics models the load buffering behavior. Before T1 writes X to R1, it can promise write 1 to Y. Next, T2 reads T1's promise to get the value 1. Then, T2 writes the value of R2 to X, and T1 reads such memory write on X. Finally, the thread T1 actually performs write 1 to Y. Note, a thread can promise a write only if the promise can be certified to avoid out-of-thin-air read. Next, we introduce our thread local simulation. The classic compilation correctness is that the target program T compiled has no more observable behaviors than the source program S. To prove the correctness, we usually establish a simulation between T and S. It means that when T takes a step, S can take 0 or more steps, and the simulation still holds. And if T generates an observable event, S generates the same observable event. However, the simulation shown here relates the whole programs and does not support separate compilation. Consider the following condition. The whole program consists of two components, S1 and S2 executing concurrently. Here, comp1 compiles S1 to T1, and comp2 compiles S2 to T2 separately. We hope to establish a whole program simulation by verifying comp1 and comp2 separately. For this purpose, we need to establish the simulations for single threads, called thread local simulation, between T1 and S1 and between T2 and S2 respectively. However, the question is how to define the simulation for single threads. Unlike the whole program simulation, when establishing the simulation between T1 and S1, program will switch to other threads at some program points, and the simulation needs to take into account the interactions with the environment. However, how do we consider the environment interference in the thread local simulation without seeing the codes of other threads? Our approach here is using an invariant as an abstraction of environment behaviors. Specifically, our thread local simulation takes an invariant I as a parameter. The invariant I specifies the consistency of the target and the source states, including the timestamp mapping and the value consistency of the target and the source messages, 1, T1, and S1 switching out. The environment behaviors should preserve the invariant I, so when switching back, the invariant I still holds. With the invariant I, we don't need to care of the specific codes of the environment, and just care about the definition of the invariant I. In our work, we allow the invariant I to be instantiated. However, I can be difficult to define in practice. First, if the interference of other threads is so frequent, the state's consistency has to be weak, since the consistency is required to hold at too many points. Consider that if the interleaving occurs at every program point, the invariant I need to hold at every point. Second, the behavior of the environment may be complicated. For example, other threads may perform receive reads and writes concurrently. Too complicated environment behavior will make it difficult to preserve the invariant I unless I is made overly weak. To solve such two problems, we introduce two techniques respectively. A non-preemptive semantics to reduce interleaving, and only allowing read-free source programs. We first introduce the non-preemptive semantics. The non-preemptive semantics has less interleaving than the permission semantics. Consider the following program. The thread can switch at any point in the permission semantics. But for the same program in the non-preemptive semantics, thread switching is only permitted at specific points. The points are after executing atomic primitives and after generating observable events. The non-preemptive semantics in our work is equivalent to the permission semantics. Define the thread local simulation on the non-preemptive semantics allows the invariant I to hold at fewer points than on the permission semantics. In our thread local simulation, if a program point is not a switch point, I does not need to hold, since there is no interference of other threads. Finally, we introduce read freedom. A straightforward definition of read in the permission semantics is that when a thread makes a write, it can see other threads writing in the same locations, as well as the premises of other threads. However, this straightforward definition would view too many programs as RISC, including the following one, which should be RISC-free. To revise the straightforward definition, we require RISCs to be checked only when premises are certified. The detailed explanation can be found in our paper. However, we allow the source program to have read-write RISCs. It's critical to support optimizations which may introduce read-write RISCs such as loop invariant code motion. The code optimized by these optimizations may become the source code for subsequent optimization passes. Consider that the source program S is optimized by loop invariant code motion and dead code elimination successively. Loop invariant code motion may introduce read-write RISCs, and the intermediate code M may contain read-write RISCs. To prove the correctness of subsequent optimizations, such as dead code elimination in this example, we must allow source programs to have read-write RISCs. Conclusion: we develop a verification framework for optimizations in the permission semantics 2.1. We verify 4 optimizations in our framework. All proofs has been mechanized in Cork. Thank you.
So I saw like you have verified two classical data flow optimizations that are there in compilers, like common sub expression elimination and dead coding. So will your techniques work here for data flow optimizations in general, or is it catered towards these two optimizations specifically?
Yes. First, I want to say that we have discussions the application and the limitation of our approach in our paper. Okay, if you want to see the more detail, you can find the discussion in our paper. And now I want to briefly answer this question. First, we have studied many real-world compilers such as Concurrent. Concurrent has we have the four optimizations we verified has focused all the data flow analysis in the Concurrent. And for the LVM, the data flow analysis in the LVM can roughly categorized into LVM roughly performs two classes of data flow analysis based optimizations such as redundancy elimination and register promotion. Yeah, our work supports the redundancy elimination optimization as we have introduced, and for the register promotion, we does not see any challenges to verify such optimizations. But our work does not consider the intra-procedure analysis based optimization or the alias analysis based alias analysis based optimizations in LVM. Okay, that's all.
Okay, thanks, Yuping. So we have a question from the audience. So Suham asks, do non-terminating loops affect the optimizations?
Yeah, it does not. It does not affect the optimization since we do not consider the compiler correctness, which is defined as the refinement relation between the target and the source, does not consider the termination preservation. Yeah.
Right. Let's thank Yuping again for a great talk and for answering questions.